Okay, good evening all. Welcome to problem solving session number 3 in the Mechanics of Material NPTEL course. So today we will see problems mostly from transformation of stress components and how to find the maximum stresses in case of 2D as well as in case of 3D. And finally, we'll see about octahedral stresses. So let's start. The first is regarding the concept of problem of transformation of stress. So I have few problems. Before going on to problem, let me quickly go through the core concept of the lecture, and then let me start with the example. So first topic that we are going to see today is the transformation of stress components. Transformation of stress components. So here, suppose if I have a basis, say Ex and Ey and Ez, and this is my current basis Ex, Ey and Ez. And suppose if I'm going to change my basis to a new basis, say Ex star, Ey star, and Ez star. I'm rotating about z axis, so z is not changing, right? And here theta is measured in anti-clockwise direction. This is very important. Theta is measured in anti-clockwise direction. Okay, I'm assuming theta as anti-clockwise direction, so that's my positive theta. So here, suppose if I have a stress tensor that is say sigma as my tensor component, say suppose sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. So this is with respect to Ex, Ey, Ez component basis. With respect to Ex, Ey, Ez basis. Now, what will happen if I rotate my basis? Will this sigma matrix will be the same or it will be different? So that's the question here. So how to find that? So if you have watched the lecture, we would have ended up in a final equation like this, that is sigma star is equal to q transpose sigma times q, where q is the transformation matrix. Okay, q transpose is equal to I, right? So this is the final thing that we need to solve the problem. So here q is equal to e I dot ej star. Okay, a star is the rotated basis, the normal is the original basis. Fine. Yeah. Now Q, how to find Q? Like suppose for this particular case that we have given, how to write Q for this case? We can write Ex star as Ex star. If we want to resolve Ex star in terms of Ex and Ey, how can we write? We can write Ex star equal to cos theta Ex. Why cos theta? Because here it's along theta. So along theta is cos theta. Opposite is sin theta. So cos theta Ex plus sin theta Ey. Okay, easy, zero easy, I'm not writing. And similarly, here we have Ey star can be written as, I want to write Ey star in terms of Ex and Ey. Maybe let me redraw this. Suppose here I have this. I want to resolve Ex and Ey in terms of Ey star. So let's do, Ex is going like this. So there will be two components of Ex. This is the Ex. So this is one component which is Ex cos theta, and there will be another component Ex sin theta, right? Now, similarly, Ex is will have Ey will have two components. Say it's going like this. Now this is theta, so this will be Ey along will be Ey cos theta, and another one will be Ey sin theta. Now we are interested in the components along Ey star. So what will come along Ey star? Ex sin theta in the opposite direction. So minus sin theta Ex plus cos theta Ey. Okay. Finally, easy star will be easy. Okay. Fine. If you are not getting anywhere, please feel free to stop me. I'll explain it again, once again. Or if I am making mistake, please let me know. I'll see it and correct it. Now, what is Q now? So Q has 9 elements in it. Q matrix, 3 by 3 matrix. So Q11 or QXX will be EX dotted with EX star, right? What is Ex dotted with Ex star? Cos theta. Similarly, Qxy will be Ex dotted with Ey star. So Ex dotted with Ey star will be minus sin theta, right? Minus sin theta. What is Qxz? Ex dotted with Ez star. Ex is there, Ez star is so 0. So similarly, when we write this Q matrix, how we will get, I have just done the first row. Similarly, you can do second and third row. So cos theta minus sin theta 0, then sin theta cos theta 0 0 0 1, right? So this is my Q matrix. Okay, these things we have to know before proceeding further. Okay, the final transformed stress component will be Q transpose sigma times Q. Okay, how this comes? We have the initial derivation in the initial notation form. You can watch lecture number 1 of this week to know more about it in detail. Okay, so let's move forward with a problem. And I just want to add one more thing here. Suppose if I change my basis, something will never change in a tensor component. In any tensor, if I change the basis, something will never change. What is that something? There are three things like that. We have to note it separately. Number one is the trace. The trace will never change when we rotate. The trace of sigma will be equal to trace of sigma. What is trace, by the way? It's nothing but the sum of diagonal elements. Okay, trace is nothing but sum of diagonal elements. So trace will never change, number one. Number two, determinant of sigma will be always equal to determinant of sigma star. Okay, it's like in a vector, if I change the basis, my vector magnitude won't change. It will always be the same. In the same way, in a tensor, there will be three things which will be the same if you change the basis, if you play with the basis. So what are those three things? Number one, the trace. Number two, the determinant. Number three is the trace of sigma square. Trace of sigma square will be equal to trace of sigma star square. We'll see in a problem now shortly. So these are called as invariants. Invariants. Mathematically, they are called invariants. Invariance means something which won't change, will never change. Okay. I can, we'll see shortly. We can play around with the stress matrix, but these three will never change. Let's quickly jump into a problem. Say, suppose problem number one for today. We are given plane stress. So what do you mean by plane stress? The z component is 0, only x and y are there. So here we have, this is the question, 5, 5, 7, 7, and we also have shear. Shear is 8. Maybe it is in mega Pascal. So I'm not writing the unit. This is 8, 8, 8. So all four sides are 8. So this is a question. This is given. Okay. Now what we have to find is, so this is given with respect to Ex and Ey basis, standard basis. Ex and Ey. Now what we have to find, what is the stress? Suppose when I change this, maybe use another color. Here I have another plane where my angle is say 60 degree from the x-axis. Okay, in measured in anti-clockwise direction. Anti-clockwise direction. So we can cut this plane, right? We can cut this plane. When we cut this plane, it will come like this. So it will come like this, it will come like this. So here we will have some traction, some normal traction, some shear traction. So you will have some sigma in, say, this is my new basis, right? What my basis is sigma x star, say assume sigma x star y star. So my rotated basis is, let me use green color. This is my rotated basis, sigma x star 60 degree. Similarly, sigma y star, sorry, ex star, ey star 60 degree. Now here we will have its own sigma components, that is sigma x star, sigma y star y star, again sigma y star x star. All the components will be there if we draw a stress state at that plane, right? So now we are interested in finding what will be the components of stress in that plane. Let's proceed. So first, let's write sigma in matrix form. So sigma xx is plus 5, sigma xyy is 7, and sigma xy is 8, and sigma, again this is 8. Both are same, symmetric. Fine. Now what is Q matrix for this problem? Q matrix is, we just saw, if it is a anti-clockwise rotation, cos theta minus sin theta, cos theta. This is only, I'm writing 2 by 2. Let's do sigma x star is equal to Q transpose sigma q. Okay, so this is equal to cos theta is 60 degree. So cos 60, I'm writing in transpose form. So sine 60 minus sine 60 cos 60 times 5, 8, 8, 7, again cos 60 minus sine 60, sine 60 and cos 60. So let's do just convert cos 60 is 0.5, sine 60 is 0.866 minus 0.866, 0.5, 5887, 0.5 minus 0.866, 0.866. Let's do in MATLAB this computation. Not MATLAB, not required, but still. Sorry, there was a network issue, so I got disconnected. I'm doing this in MATLAB. So we have three matrices. Say Q matrix is Q matrix is zero point 0.5.
The screen not visible, sir.
My calculator screen not visible.
No, sir.
Oh, can you recheck, sir? Once now. Calculator screen
Yes, sir. Visible.
visible, right? So minus 0.5 minus 0.866. First row done. Second row 0.866 and zero point 0.5. This is my Q matrix. And sigma matrix is sigma equal to 5, 8, 8, 7. 5887. Now what we want? Sigma star. Sigma star is equal to, as per the formula, Q transpose times sigma times Q. Okay, just matrix multiplication instead of a normal calculator. I'm using MATLAB here. Okay, so I'm getting the sigma star. I'm going noting down and going back to my notepad. So sigma star is 13.4277 minus 3.1336 minus 3.1336 again and minus 1.4282. So this is my sigma star. Okay. I hope you're also getting the same, sir. If there is any error, also you can let me know. Suppose if you are not getting the same, Fine. Now, let me go back to this normal screen. I hope my normal screen is visible now.
Some same MATLAB screen is there.
Okay. Fine. Now, sir.
Yes, sir, visible.
So fine. So this is sigma star. Now the question is, we can write sigma x star as 13.4277, sigma x star y star as minus 3.1336, and sigma y star as minus 1.4282. Okay, now let's check whether those three invariants remain the same or not. What is trace of sigma? First invariant was trace of sigma. Trace. So trace of sigma and trace of sigma star. Let's find out. The trace of sigma was 5 plus 7 equal to 5 plus 7, which is 12. Here, trace of sigma star would be 13.4277 minus 1.4282. So, which is how much? 13 minus 1, 12. So, it is 12 exactly, nearly 12. Fine. Next, what were the other one? Determinant of sigma, determinant of sigma will be equal to determinant of sigma star, right? So determinant of sigma was 5 sevens are 35 minus 64. 35 minus 64. 29 minus 29. What is determinant of sigma star? We can check it. 13. This needs some computation. 13.4277 into minus 1.4282 minus 3.1336 the whole square. So this will also be minus 29, right? Fine. And third invariant was trace of sigma square. Trace of sigma square. So here sigma square, how we have to find sigma into sigma. Sigma square is sigma times sigma. So that is 5887. 5887 times 5887, which is 25 plus 64, 89, and 40 plus 56, 96, and 40 plus 56 again, and 64 plus 49, 64 plus 49, 103. So trace of sigma square will be 89 plus 103. 189, 192. Fine. Similarly, when we find the trace of sigma star square, we will get 100. We should get 109. We can use this as a check whether our problem is correct or not. Okay, so this is the first concept for today. The concept was uh, when we change the stress component from one basis to another basis, three invariants won't change. Uh, Even though the components, the nine components of a 3 by 3 stress tensor changes, three invariants like number one, the determinant, number one, the trace of sigma, number two, the determinant, number two, three, the trace of sigma square. These three will remain the same irrespective of the basis. Fine. So let's proceed. Now let's draw the Mohr circle for the same, or maybe we'll solve another problem and we'll go to Mohr circle. Suppose if we have this is problem number two, if we have a stress state given by Ex, Ey basis. So here it's 80, 80, and shear is 30. Shear is 30. 30. Fine. They have given the new basis Ex star, Ey star, Ex star, Ey star, and Ez star. All they have rotated by 60-degree in clockwise rotation. In clockwise rotation. So we have to make a note. Clockwise rotation about z axis. Okay, so this is a question. Now we need to find what will be my stress or the tensor components in the new basis. That is sigma x star, sigma y star y star. The question is sigma x star equal to what? Sigma y star equal to what? Sigma x star y star equal to what? Similarly, sigma z star equal to what? And sigma x z star equal to what? So there are five subdivisions in the question, right? So this is what we have to do. Now, same thing, but here the only change from the previous problem is here they have given it is clockwise rotation. So if we are going to use this formula, this was derived assuming theta as clockwise, anti-clockwise. So we have to just substitute in the place of theta, we have to substitute minus theta. Okay, so let's proceed. First, let's find the transformation matrix. That's the first step. Finding transformation matrix. So transformation matrix was Q, which was equal to EI dotted with EJ star. This is QIJ, right? QIJ is EI dotted with EJ star. Now, what it would be? Q is equal to, in a matrix form, here same rotation, cos theta. Theta is negative, so cos of minus theta is again cos theta, minus sine of minus theta, 0, sine of minus theta, cos of minus theta, I'll write minus theta itself in one step, 0, 0, 0, 1. So this is equal to cos theta, sine theta, 0, minus sine theta, cos theta, 0, 0, 0, 1, right? So there is a change in the transformation matrix. This is transformation matrix for clockwise rotation. Whatever we derived before, that was for anti-clockwise rotation. There's a small change. The change is the negative sign. Here, the Q became Q transpose, right? When we change from clockwise to anti-clockwise. Now we can solve the problem as usual. Sigma star is equal to sigma star equal to Q transpose sigma Q. So this is equal to Q transpose. Theta is again 60 degree. So Q transpose. I am writing directly. Cos 60 is 0.5. It is a transpose, so negative here 0.866, 0.866, 0.5, 0, 0, 0, 1. This is Q transpose. Sigma is, what is sigma here in this question? First, we have to note it down. Sigma was 80. And is there any y? Okay, xy is 30 plus 30 or minus 30. On the positive explain,
Plus 30.
yes, it's pointing upwards, so correct. It's plus 30 and 0, and here also 30. And is there any sigma yy on the y plane? There is no normal stress in the y direction, so it is 0. 0, 0, and z is 0, of course, because this is plane stress state. In plane stress state, all the z components will become 0. So this is my sigma 80, 30, 30. So 80, 30, 30, 0, 0, 0, 0, 0, 0. Then again q will come. So what will happen if we multiply all these things? Let's do, we have to use calculator again. So I hope we can do. It is coming. I am writing directly the answer. Minus 6, 19.64, 19.64, 86, 0, 0, 0, 0, 0. This is the final answer. If you are doing, you should get this answer. Okay. Now, can we have a quick check whether my answer is right or wrong? What is the trace of sigma star? Trace of sigma star is 86 minus 6 is 80, right? Now, trace of sigma is again 80 plus 0 is 80, correct? And again, sigma square is difficult. It needs more computation. Determinant would be 0. There also determinant would be 0, right? Because one column or one row is 0 fully. So determinant would be 0 always for a plane stress. So it's moreover correct. If you want it to be more accurate, confidently you want to say, then you can check trace of sigma square equal to trace of sigma star square. Okay, this is the, so the answer to the question is my sigma x star is sigma x star is sigma x star is minus 6. Sigma y star is 86. Sigma x star y star is 19.64, and all the sigma x star z star everything is 0. Okay, remaining thing are 0. Okay, that's it. So this finishes the first part of the uh, top problem for today. Okay, all that we have seen so far is only transformation of stress component. When we how a tensor will change its component when we change from one basis to another basis. Fine. Let's move on to the second part for today. The second part for today is finding extremum stresses for a plane stress condition. So, yeah, extreme values of stress for a plane stress condition. Plane stress condition is easy, little. And before that, we also have to see Mohs circle and Mohs circle also we have to see. Now, actually, um, if we transform the stresses from ex ey ez to ex star ey star ez star, we would have got an expression for sigma x star, sigma y star, sigma x star y star. What it was like here itself, we should have written it, but fine. So sigma, if we multiplied that. Sigma star was sigma q transpose sigma q. Like if we multiplied that, we would have got an expression like this. Sigma x star expression was sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta plus sigma xy sine 2 theta. Okay. And similarly, sigma x star y star was sigma xy cos 2 theta plus sigma yy minus sigma, that's a sign change, sine 2 theta. Okay, these were. Suppose if we want again sigma y star, same sigma xx plus sigma yy by 2 minus sigma xx minus sigma yy by 2 cos 2 theta minus sigma xy sine 2 theta. This is easily we can derive using the Q matrix and the sigma matrix. When we multiply all the three matrices, finally we will end up in this equation, in these equations, right? And here also we can note the trace of sigma will be same. Sigma xx plus sigma yy will be equal to, when we add this sigma x star sigma y star, this the second term and third term will cancel each other. First term will add up. So sigma xx plus sigma yy by 2, two times coming. So it will be sigma xx plus sigma yy. So that is nothing but trace of sigma star. Okay. So this is what we have seen so far. Now, like the concept of Mohs circle is very simple. From these equations, from these stress transformation equations, we will do some mathematical manipulation to write in the form of an equation of a circle. And once if we can do that, we can represent a stress state using a circle, a point in a circle. For example, in the first equation, when we shift this first term to the left side and when we square them and some add it up with the second equation, again doing square, putting the first term to the left side, we will finally end up in an equation of circle like this, right? That is sigma x star minus sigma xx plus sigma yy by 2 to the whole square plus sigma x star y star minus 0 to the whole square is equal to sigma xx minus sigma y by 2 the whole square plus sigma xy square. So this is equation of a circle where we have x minus h the whole square plus y minus k the whole square equal to r square. H comma k is the center of the circle, r is the radius of the circle. So here h comma k or center of the circle, center is sigma xx plus sigma yy by 2 comma 0, and radius is sigma xx minus sigma yy by 2 the whole square plus sigma xy square, right? There is a square root. R square is the right side quantity, so there is a square root. Fine. So this is equation for Mohr circle. Now we can draw this in the form of a circle, like the this stress state also we can represent. If you want to draw Mohr circle for this stress, uh, let me copy this. Suppose if I want to draw the Mohr circle for this particular stress state, how will we draw? Using these equations, let's do. Yeah. So here first x-axis. My x-axis here is sigma x star, the normal stress, or y star, both the normal stresses. So this is my sigma x star or y star is a normal stress, and y axis is shear sigma x star y star. Okay. Now the center of the circle was sigma xx plus sigma yy by 2. Say suppose this, if this is my sigma xx and if this is my sigma yy on the x-axis, so my center will come somewhere here. And we have to get the radius, this radius. So assume sigma xy is positive on this plane. So here and here, when we, this is sigma xy, we have to join this. Now we got the diameter, right? Because this is the radius, this hypotenuse is the radius, and we can get the radius as this distance is sigma xx minus sigma yy by 2, right? This distance. Sigma xx minus sigma yy by 2, the whole square, plus sigma xy, the whole square. So this is the radius, and hence we can draw the circle and get the Mohr circle. Okay, and now if we draw a Mohr circle, there will be 2 points where we cut with the x-axis. There only normal stress is there. There's no shear stress. So those 2 points we call sigma max and sigma min, maximum stress and minimum stress. They are called as principal stresses. So where only normal stress will be there, it will be maximum, and shear stress will be 0. And similarly, there is a point where the shear stress is maximum, but normal stress not necessarily 0, right? There is a normal stress at the point where shear stress is maximum. Now, for this particular question that we have, if you want to draw this Mohr circle, this is 80. So sigma xx is 80. First sigma xx, say assume here 80. Sigma yy is 0. So here sigma yy. From sigma xx, I have positive shear. So I'll go up 30, 30. And yy also, I have negative shear. 30, 30. Now, when we join these two, we will get a diameter. So they will intersect the x-axis at the center correctly. This is center. Now we can draw the circle, more circle for this using the radius. Sorry, the circle is not coming properly. It's looking like a oval. Assume it is a circle. So this is sigma 1 or sigma max. This is sigma minimum. Okay. So this is more circle for our problem. Now let's go to the extremum stresses problem based on extremum stresses. So we are given a stress state and we are asked to find few of the questions. Number one, the magnitude of the principal stress, and then orientation of the principal plane, and magnitude of the shear stress. For all these, we have a expression like we can do the same thing analytically also. Take the expression for sigma x star and do find the derivative with respect to theta because we want theta. What is theta? If it is 0, finally we can get the plane where the maximum normal stress is there. So tan 2 theta p will be sigma xy by sigma xx minus sigma yy by 2. Okay. Here, like this, 2 theta p, this angle, because this is sigma xy, this is sigma y xx minus sigma yy by 2, right? Opposite by adjacent is tan. And similarly, we can do sigma x star y star by d theta equals 0, and we can get the tan 2 theta s sigma x star y star by d theta equal to 0, and when we do, we will get tan 2 theta s as 2 times sigma x x minus sigma y negative of it by 2 times sigma xy. Okay, right? And when we substitute this tan 2 theta p in sigma xx and sigma yy, we can again get the values for principal stresses. So I'm writing the analytical expression sigma 1 comma 2. 1 is the maximum, 2 is the minimum, assume. So this is equal to sigma xx plus sigma yy by 2. Again, plus or minus. Plus is for maximum, minus is for minimum. Sigma xx minus sigma yy by 2 the whole square plus sigma xy to the whole square, right? And sigma xy max, the shear stress maximum, is nothing but the radius there, right? Radius in the Mohs circle. Sigma xx minus sigma yy by 2 the whole square plus sigma xy the whole square, right? This hypotenuse side. Similarly, my principal stresses are this point, so my distance from here to here will come. This is what this distance is. So, sigma xx plus sigma yy by 2, that is from here to center, sigma xx plus sigma yy by 2 plus the radius. Radius is this. Okay. And similarly, the other one is minus of that. Fine. So this is sigma expression for principal stresses and shear stresses, and expression for angle orientation of principal stress with the x-axis, and the shear stress plane with the x-axis. Now we'll solve problem based on these expressions. Let me write the question. So we can take the same question, or yeah, let me take this question. The problem number 2 is here. Assume this is number 3 because more circle. And number 4, problem number 4 for the day. So given we have a plane stress state, 60, 60, 120, 120, and this is 40, it's also 40, 40. Okay, this is given. Now we'll find one by one. So the first question, what is the maximum normal stress? Okay. So a body, some body is there. It is subjected to some stresses. It can be due to load acting over it. It can be due to a support, a spring support or a hinge support, roller support, or it can be due to anything. Some load is acting over a body. Now we need to find, we are only interested in the maximum stresses. Why? Because for design purpose, for anything, we will only take the maximum value and we move forward with the design. So which one will be maximum value? The principal stresses will be the maximum value, right? So it will be in some other plane, and we just saw, we can write this tensor in this form like 120, 40, 40, 60, 0, 0, 0, 0, 0. This is just tensor. Now, when I change, this is EX-EY basis, which is here standard EX-EY. Now, when I change this basis to some EX star, EY star, I will have n number of bases. I can take anything I want. Uh, like this one or this one, any basis can come. So each of the bases will have its own stress tensor. Fine. There will be one plane, one, see, each basis corresponds to each plane. So there will be one plane where only normal stress will be there. There won't be any shear stress. So that is the plane where the normal stress is also maximum, because this is proved in analytically also, and this is true for any body, for that matter, we can take. So that plane, if we take the stress tensor, we'll get something like this. Everything will be zero, okay, except sigma 1 1. See, in this problem it is 0 because it's a plane stress, so sigma 3 is 0. But otherwise we will get a stress state like this. So this is also same. Okay, this is also a same sigma, but it's sigma star in some other basis. Some other basis. Which basis? The principal basis, the eigen basis, the basis where the normal, the principal stresses acts. Okay, fine. There are hundreds of possibilities. Now, we are going to find what is that basis. Here we already have the expression, so we can directly substitute and we can find. So first sigma 1 is sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 to the whole square plus sigma xy to the whole square. This is equal to 120 plus 60 by 2 plus or minus 112. Let me do parallelly. 120 minus 60 by 2 the whole square plus 40 the whole square. This is equal to 120 plus 60, 180, 180 by 2, 90 plus or minus 120 minus 60, 60, 60 by 2, 30, 30 square plus 40 square. This is equal to 90 plus or minus 30 square plus 40 square is 50 square root of, so 50, right? This is equal to 90 plus 50 is 1 and 90 minus 50 is the other one. So 140 comma 40. So the maximum principal stress sigma n max or maximum normal stress is 140. Unit is megapascal or whatever unit given in the question. Sigma min is 40. Okay. This this solves the first part, first question. Maximum and minimum. So this tells us the value. It is 140. Hmm. Now let's move on to the next question. Next question is maximum shear stress. Magnitude of the maximum shear stress. What is the maximum shear stress magnitude? The formula was sigma x star y star max. In terms of that xxyy, this formula is there, but in terms of principal stresses, we have a simple formula. First, we'll do this sigma xx and a sigma yy by 2 the whole square plus sigma xy the whole square. That is 120 60 and 20 minus 60 by 2 the whole square plus 40 square. 120 minus 60, 60, 60 by 2 is 30, 30 is 50. So 50 is the maximum shear stress. Or we can directly use the principal stresses formula, sigma x star y star max is equal to 140 minus 40 divided by 2. Sigma 1 minus sigma 3 by 2, or sigma max minus sigma min by 2, which is 50. Okay. And the next question. Next question, they are asking to find the plane, find the orientation of the, find the orientation of the plane where maximum normal stress occurs. Right. So what is the orientation formula? Tan 2 to theta p equal to 2 sigma xy by sigma xx minus sigma yy. Tan 2 theta p is equal to 2 times sigma xy in this problem was 40 by 120 minus 60. 80 by 60. 4 by 3. So tan 2 theta p is 4 by 3. Let me use calculator. Inverse of inverse tan calculator. Tan inverse of 4 by 3 is 4 by 3 is 1.3. 52.4 degrees I'm getting. So 2 theta p is 52.4 degrees. Now theta p will be 26.2 degrees. Okay, that's it. Now here, since both are positive, it is in the first quadrant, so it's direct. If suppose if any one is negative, like numerator denominator, if numerator is negative or denominator negative, we have to check the quadrant accordingly. First quadrant, second quadrant, third quadrant, fourth quadrant. So theta is 0 to 90, 180, 270, then 360. So the domain of theta is 0 to 360. Right? But when we do in our calculators, it will give us 0 to 90. That alone we have to take care of. Right? Fine. This is the plane for maximum normal stress. And next question, next part of the question. Magnitude of, no, it's done. Maximum shear stress value. Okay. Magnitude of shear stress where maximum normal stress occur, so how to find this? Where maximum normal stress occurs in theta p is 26.2 degree with the x-axis. So when we substitute that, we'll get the shear stress has 0, because in the plane of maximum normal stress, the shear stress directly goes to 0. Sigma xy equal to 0 at principal planes. Okay. This is direct for any of the problem. And magnitude of normal stress at which maximum shear stress occurs. Yes. So This one, we already got the tan 2 theta s. Like when we substitute that in the sigma x expression, we got sigma x star as sigma xx plus sigma yy by 2, right? This is the formula. Now, in our case, sigma xx and sigma yy was 120 and 60. This is equal to 120 plus 60 by 2, 90. This is maximum normal stress. So the point to note, when the normal stress is maximum, shear stress goes to zero. But when shear stress is maximum, normal stress need not be zero. It can be there or cannot be there. Okay. And finally, they are asking about the state of stress. So, state of stress, we have uniaxial state of stress, biaxial state of stress, deviatory state of stress, and plane state of stress. So, also pure shear state of stress. So, based on the stress tensor. So, is this tensor a uniaxial state of stress? The first question. For uniaxial state of stress, the determinant must be 0, and pure shear state of stress, the trace must be 0, right? And plane state of stress, again determinant is 0. So this we can simply say determinant is 0 because hence it is a plane state of stress. Okay. If trace is 0, it's pure shear. And if again, if it is only along one axis, it's uniaxial state of stress. Fine. Okay, so this completes the 2D part. Maybe we'll also, for closure, we'll also draw the Mohr circle for the scene and we'll complete for the same problem that we have seen. So here sigma x 120, 40, 60. So 120 is sigma xx, 120, and 60 is sigma yy, and 40 is sigma xy, 40 and 40. And this would be 800, right? 100. By the way, this is sigma axis. This is tau axis or sigma xy axis. This is sigma xx or sigma yy axis. Now, when we draw this, we'll get a diameter like this. And so this radius would be, this is 20, this is 40. So radius is root of 40 square plus 20 square. So 1600 plus 2000. 20 into 100. 10 root 20. Is that right or any mistake? Because last time we got radius different, 50. So where is the mistake? Did I note down the question correctly? 120, 40, 60. 120, 60, 40. Correct. So this is 20, this is 20. Let me find this value. 44.72 I'm getting. But this radius should be equal to the maximum shear stress, right? So we should get 50, right, as per this question. Sir, are you seeing any mistake?
I'm checking, sir.
Uh, Sigma xx minus sigma yy by 2 the whole square plus sigma 120 minus 60 is 60 by 2 30 plus 40. So 120 minus 60. Okay. Oh, sorry. So the center is the problem. This is not 100. The center is 90. This is 90. So this distance is 30, not 20. This is 30. So now we will get 900, 2500. So radius is 50, which is the maximum shear. So max is sigma max is the radius plus this distance. This distance plus the radius. What is this distance? Is this distance already the center, which is 90 plus 50, which is 140. Same answer. Sigma min, sigma min is only this distance. This distance. This is max. So minimum is center minus the radius. 90 minus 50, which is 40. Correct. Fine. And what else we can observe? This point is this plane is, we know this is our EX EY plane, and my maximum normal stress is this plane, and from here to here it is some 2 theta p in the clockwise direction, right? We can measure, if I am drawing this Mohr circle to scale, we can measure this angle. This would be equal to this 52.4 degrees. Okay. In Mohr circle, if it is 2 theta p, in normal it is theta p, right? Because that's how we derive the expression. Fine. That's it. So this completes the plane state of stress. Finally, the last topic for today is 3D state of stress. But before that, uh, maybe I'll quickly go through the concepts of finding normal and shear stress. And shear stress already we would have seen in the last week, like how will we find normal stress? Sigma of n is nothing but T's of n dotted with n. The traction vector projected along the plane, along the normal, is the normal stress. T's of n we can write sigma transpose n. dotted with n. And shear is given by, actually shear is a vector, so I can write total traction minus normal traction, and magnitude of this is given by T of n, the magnitude of this traction square minus normal magnitude square. Okay. Now, when we come to state of stress, since we have seen the transformations of stress, suppose if someone is giving a stress state which looks like this, phi, or let's say sigma, sigma xx, 0, 0, 0, 0, 0, 0, 0, 0, right? And another stress state which looks like this, sigma x x, sigma x x, sigma x x. So I should not write sigma x x. Let me write sigma 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 sigma. All are sigma. 1 by 3 is there, common. And there is another stress state which is given by sigma sigma 0, sigma sigma 0, 0, 0, 0, 1 by 2. So there are three stress tensor given to us. Number 1, number 2, and number 3. So all these stress sensor, if suppose if someone is giving again a loading condition, says a body is there, some bar or some longitudinal element, and if suppose this is subjected to a loading in the x-axis P, some stress in the x-axis. Now this corresponds to uniaxial state of stress. Now, suppose if someone is asking which of these three stress tensors represent this uniaxial state of stress, option 1 or option 2 or option 3, which of these three represent the uniaxial state of stress? So far, before joining this course, we would have directly said sigma xx, the first option, that is sigma xx 0, 0, because of course, right, only sigma xx is there, all the other components are 0, right? But it's not the only case, because suppose if you want to draw a Mohr circle for this stress state, how it will look like. This is sigma axis, this is tau axis, or sigma xy axis. So only one is there, sigma xx is there, right? So there is no tau xy going away. So this is my principal stress. And another is 0. Okay. Now I got the diameter. We have to draw the circle, right? So this is my circle. Now, how about this point, this point? This is also a stress state, right? This point is representing uniaxial. This point, every point on the Mohr circle is representing some plane, right? All are uniaxial state, right? Let me take this point. This is sigma xx by 2, right? Half, because totally it's a sigma xx, so the radius will be half of the diameter, the sigma xx by 2, which is actually 90-degree in Mohr circle. If it is 90-degree in Mohr circle, in reality it will be in 45 degrees, right? So when we cut a plane here, 45 degrees, 45 degrees, we will be having a stress here at this plane of 45 degree. we will be having sigma xx as well as sigma xy, because here and here. This will be if we want to compute using the previous thing, we can find a normal. The normal is 1 by root 2 ex plus 1 by root 2 ey. Okay, so using this, we can compute it is sigma xx by 2, and this also sigma xx by 2. Right. So for this plane, the stress tensor is sigma xx by 2, sigma xx by 2, 0, sigma xx by 2, sigma xx by 2, 0, 0, 0, 0. This is option 2. Option, sorry, 3. Okay, this is that option 3 is sigma xx. Fine. So this actually represents this 45-degree plane. Similarly, for this loading, I will have another plane where my this stress tensor holds true. Okay, so I will have n number of stress tensor corresponding to n number of planes where we will have everywhere it is uniaxial stress state. So we should not think like you okay uniaxial stress state means only one will be non-zero, rest will be zero. No, then how to find uniaxial stress state? So uniaxial stress state, we say here the determinant is zero. The determinant is zero is one condition, and if we can see the trace of this is sigma, the trace of this is again sigma, the trace of this is again sigma. So the trace is not changing, right? So with respect to uniaxial state of stress. So this I just want to say. Similarly, when it is a pure stress state, pure shear stress shear, there we will have trace of sigma will be zero, right? I can represent a stress sensor like zero, tau, tau, zero, 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 zero. And this doesn't mean that there is no normal stress, because if you draw the Mohs circle, sigma xx is 0, sigma yy is 0, but there is a tau, so we'll get some circle like this. So tau, right? And here there's a normal stress. So there is a plane where normal stress will be there. It need not necessarily be 0. Okay, fine. So this is regarding the state of stress. So finally, the final topic for the day is 3D state of stress. 3D state of stress. Same thing, but we are going to extend it for 3D. Let me directly go to a problem. Say, suppose uh, we have been given with some stress sensor, sigma is equal to minus 60, 40, 0, 40, 0, 40, 0, 40, 60. So this is the state of stress tensor given. Now we want to find what is the maximum principal stress, minimum principal stress, maximum shear stress, and the plane at which maximum principal stress occurs. Okay, and also finally octahedral. So we'll go one by one. Now, when it comes to 3D, just to add some concept, here sigma of n is sigma transpose n dotted with n, right? So here when we differentiate this, finally we will end up in an equation like this: sigma minus lambda times identity is equal to 0. Uh, Sigma times lambda and the n times equal to 0. So this is nothing but the eigenvalue problem. Okay, eigenvalue problem. So we need to find a lambda such that this equation holds true. So the lambda corresponds to the eigenvalues or the principal values, and the n corresponds to the principal planes or principal directions. So we will get a condition that determinant of sigma minus lambda I is equal to 0. Sigma is the stress tensor. I is the identity matrix. Lambda is some constant. So that constant will give us the principal value, eigenvalues. Okay, this we have to solve. When we solve this, we will get a cubic equation. Lambda cube, lambda square, lambda and constant. I1, K1, K2, K3. They are invariants. So K1, K2, and K3. Plus minus plus minus. So this is an equation, cubic equation. Like we can solve this, right? Solving it, we will get it. So K1 is, as we saw before, first invariant, that is trace of sigma. K3 is determinant of sigma, but instead of trace of sigma square, here when we do the computation, we will end up in half trace of sigma the whole square minus trace of sigma square. Okay, these are three invariants, principal invariants they are called, which arise in the principal stresses problem. Okay, so these three won't change irrespective of any basis. So we have to find K1, K2, K3. Then we have to solve this cubic equation. Once if we solve this cubic equation, we'll get the lambda 1, lambda 2, lambda 3. They are nothing but the principal stresses. Once we get lambda 1, lambda 2, lambda 3, we go back and substitute in this equation for n1, n2, n3 with the condition that nx the magnitude is 1. They are orthonormal, right? Eigen vectors are orthonormal vectors. So with that, we'll solve the problem. So now let's move forward. The question that we have been given with is a stress tensor, problem number 5, right? Problem number 5, last problem. Yeah, problem number 5. Now let's solve. Yeah, this is equal to, first what we have to find, we have to find the principal stresses. So principal stresses, we know from the derivation, sigma minus lambda times identity determinant, or this times some n vector equal to 0 vector, right? 0. So this implies determinant of sigma minus lambda times identity is equal to 0. Now this is equal to, let's move forward, minus 60 minus lambda times I. Okay, this we will have two matrices, minus 60 minus lambda 40 0 40 minus lambda 40, 0, 40, 60 minus lambda. Now determinant of this is 0. So this will give rise to lambda cube minus this k1 lambda square plus k2 lambda minus k3 equals. You can solve this itself, but since I know the form, I'm directly writing this. So what is k1? K1 is trace of sigma. Trace of sigma is minus 60 plus 60 is 0. Okay, trace of sigma is 0. It's a pure shear, right? K2 is 1 half trace of sigma the whole square minus trace of sigma square. Oh, this we have to find trace of sigma the whole square 0. Trace of sigma square. Sigma square we have to find. Sigma square is what? Minus 60, 40. 40, 0. 0, 40. 0, 40, 60. Times minus 60, 40, 0, 40, 0, 40, 0, 40, 60. I hope I didn't make any mistake in copying. Minus 60, 40, 0, 40, 0, 40, 0, 40, 60. Again, same. Correct. So let's find this is equal to 3600 plus 1600 minus 2400 plus 0 and again 1600 0. This is second row first column minus 2400, second row second column 1600 plus 1600, third second row third column 0 plus 0 plus 2400, and third row third column I'll directly do 1600 plus 3600. Actually, we are interested only in the trace. So, trace of sigma square is this plus this plus this. This is equal to 3000. Just add everything. So, 7200 plus 1600 times 1, 2, 3, 4. 200 plus 6400. 6, 13, 13,600. So trace of this is trace of sigma square. Okay. Now what is K2 now? K2 will be therefore K2 is half 0 minus 13,600. So this is equal to 6 6 8 6,800. Okay, correct? Is it correct? This is K2. Finally, K3 will be determinant of sigma. K3 will be determinant of sigma minus 60, 40, 0, 40, 0, 40, 0, 40, 60. Minus 60 times 0 minus 1600 minus 40 times 2400 minus 0 plus 0. This is equal to 96000 again minus 960. So this is 0, right? Determinant is 0. Okay, so let's go back to the cubic equation. The characteristic, this, by the way, this is called characteristic equation. So, so lambda cube minus k1 is 0, 0 lambda square is done, and k2 is minus 6800 lambda again equal to 0. Okay, this is we have to solve. This is equal to lambda times lambda square minus 6800 is equal to 0. So one is lambda equal to 0, another is lambda equal to plus or minus root of 6800. 6800 square root 82.46. 82.46 plus and minus 82.46. Okay, so the three principal stresses are 82.46, 0 minus 82.46. Okay, so these are three principal stresses, right? The maximum is 82.46, again the minimum is negative 82.46. Fine. So actually, this stress state tensor that they gave is same as this stress tensor 82.46 0 0 0 0 0 0 0 minus 82.46, right? This is in eigenbasis sigma n. Okay, in eigenbasis or in principal basis. Fine. Okay. We can check it. Trace of sigma will be equal to trace of sigma in this basis. Number one. Again, trace of sigma square will also be same. So same representation, but this plane is at some degree that we'll find it now. But I'm just telling this stress sensor is same as this stress tensor. And next question is orientation of principal plane. The x component, y component, z component. Next question is x component, y component, z component of the normal to the plane where or on which maximum normal stress occurs. Plane on which sigma max occurs. Okay, where sigma max occurs here, sigma max is 82.46. So for lambda equal to 82.46, we have to substitute back into this equation. This equation. So let's substitute back. So here, here we are finding the principal direction. So sigma minus lambda I n is equal to 0. This is the equation, eigenvalue problem that we had. So sigma is 60, minus 60, 40, 40. Minus 60, 40, 40, 0, 0, 0. And we also add minus lambda, right? Minus lambda. And what else? 40, 0, 40, 60 minus lambda. 0, 40, 60 minus lambda. Yeah. And there's another 40 above. This is not 0, 40. I hope this is correct, right? Question. This times, I'll write this as nx1, ny1, nz1 is equal to 0, 0, 0. Okay. Fine, I'm just writing this, substituting this equation, sigma minus lambda. Now we have to find the plane at which maximum normal stress occurs. So maximum normal stress occurs at lambda equal to lambda 1. So for lambda equal to lambda 1 is the maximum value, which is 82.46. 82.46. What will this equation becomes? This equation will become minus 60 minus 60, 82.46, 82.46 minus 60 is giving me 22.46. 40, 0, 40 minus 82.46, 40, 0, 40, 22.46. Here it will become 142, right? Minus 6 minus 142.46 times nx1, ny1, nz1 is equal to 0, 0, 0. Now, when we solve this, we'll get three equations, three unknowns. So, solving that, we will get the x component, y component, and the z component. And also, they have to satisfy one more condition: the nx1 square plus ny1 square plus nz1 square should be equal to 1. They are, this is another condition we have to impose on the planes. Okay, so minus 142.46 nx1 plus 40 ny1 is equal to 0. 40 ny1, sorry, 40 nx1 minus 82.46 ny1 plus 40 nz1 is equal to 0, and 40 ny1 minus 22.46 nz1 is equal to 0. So let's take this as 1, 2, 3. Maybe from equation number 3, 40 ny1 will be equal to 22.46 nz1. So ny1 I can substitute 22.46 divided by 40. 0.5615. 0.5615 nz1. Okay. This is equation number 4. What else? From equation number 1. Equation number 1. minus 142.46 nx1 will be minus 40 ny1. Now again ny1 can be given as 142.46 divided by 40, 3.56. 3.56 nx1. Equation number 5. Can we substitute this in equation number 2 so that we will get ny1? So 40 times nx1. Uh, okay, I have to write everything in terms of a single variable so that it is easy for me to substitute. Instead of this, I can write nx1 as 1 by reciprocal of this is 0.281, 0.281 ny1, and this is equation number 5 implies. Similarly, 4 implies nz1 is nothing but 1 by 0.5615. This is 1.78, 1.781 ny1. Now I can substitute now this 6 and 7, 6 and 7 in equation number 2. What will happen? Implies 40 times 0.281 ny1 minus 82.46 ny1 plus 40 times 1.781 ny1 is equal to 0. So what we get? 40 times 0.281 is 11.24 ny1 minus 82.46 ny1, and 40 times 1.781, 71.24 ny1 equal to 0 plus 11.24. So this is equal to 0, equal to 0. Why it's coming like this? Because in this eigen problem, the usual approach, like we cannot solve these three equations for a unique solution, right? Because right from the beginning, we assumed that determinant of sigma minus lambda is 0. So there are many solutions, right? There is no unique solution, right? So that Chuma, I have solved by this way so that we will know why we cannot solve this. Like if you try to solve this eigenvalue problem using only these three equations, no way we will get a unique solution. We'll usually end up in something like this. Okay, independent out of these three equations, two are independent, one is dependent over the other two, so we cannot solve. So what we have to do, now only we have to use this condition, this nx square plus ny square plus nz square equal to 1, right? So let's substitute there. This is equation A. So substitute my nx and nz in, that is 6 and 7 in A. That implies nx1 square plus ny1 square plus nz1 square equal to 1, right? So that is equal to 0.281 ny1 square plus ny1 square plus 1.781 ny1 square equal to 1. So this implies, let's do 0.281 square plus 1 square plus 1.781 square. This gives me 4.25 251 ny1 square equal to 1. That implies reciprocal of this is ny1 square equal to 0.235. So ny1 will be square root of this 0.48. Okay, 0.485. So 0.49. I can round off. Plus or minus. Okay, since it's a square root. So for each value, similarly, when we substitute this ny in nx, therefore nx will come around, that is nx 0.281. This times 0.281. 0.14 I am getting. Similarly, nz1 is 1.781 times. 1.781 times 0.49. 0.87 I'm getting. Okay, so the plane is the plane that we want. This is my x component, this is my y component. This is the question. Okay, this is the answer to the question. The plane that we want is 0.14, 0.49, 0.87. This is 1, or minus 0.14, minus 0.49, minus 0.87. Of course, right? There will be opposite plane always. If there is x x plane over here, there will be a negative x pointing the opposite direction. So this is what it means. There's an outward normal n here. There's an outward normal in the opposite direction. These two are those norms. Fine. So this is how we'll solve a 3D stress problem. Okay. Similarly, we can move forward in finding the maximum shear stress also. We have a formula for finding maximum shear stress, tau max. Tau max is equal to tau max equal to sigma 1 minus sigma 3 by 2. Actually, we have to check for sigma 1 minus sigma 2 by 2, sigma 1 minus sigma 3 by 2, and sigma 2 minus sigma 3 by 2. Out of the three, which one is the maximum of the maximum will give us the maximum, overall maximum. So here, sigma 2 is 0. So I know it is sigma 1 minus sigma 3 by 2, right? Because sigma 2 is 0. So no need to do all these things. So directly we can write 82.46. So that is say 82.46. Minus of minus will become plus 82.46 by 2. This is 82.46. Okay, this is my Tomax. Okay, and what is the magnitude of normal stress on the plane where shear stress is maximum, and similarly shear stress on maximum normal stress, that we can find, right? Because shear stress on maximum normal stress is always 0. And finally, we let me just close with the octahedral uh, plane. So octahedral normal stress, octahedral on the octahedral plane, what is the normal stress? What is the shear stress? Now, octahedral plane is nothing but the plane where my normal is equivalent to it makes the equal angle with respect to the principal directions. Uh, the octahedral plane, for example, this normal is given by 1 by root 3 n1 plus or minus n2 plus or minus n3. Okay, this is the octahedral plane. Now, if we move forward in finding the traction and the normal, I'm directly writing the final expression, which is we'll get k1 by 3, where k1 is the trace of sigma, sigma 1 plus sigma 2 plus sigma 3 by t. This is normal stress. So in our problem above, we know sigma 1, sigma 2, sigma 3. So sigma 1, sigma 2, sigma 3 is what? 82.45 plus 0 plus minus 82.45. So all will add up to 0, right? So this will become 0 in our case. Okay, octahedral normal stress is 0. And for shear, the formula we will get while deriving is tau octahedral square is equal to trace of sigma square by 3 minus trace of sigma the whole square by 9. Okay, this is we'll get. Now we can move forward in finding the trace of sigma. Trace of sigma here is 0, right? Already we have found. Trace of sigma is 0 and trace of sigma square is 13,600 we have found out. So this is equal to 0 minus trace of sigma square is 13,600 by 3 minus 0. So this is nothing but 13,600 by 3. 4,550. This is square root of 67. 3. Right, that's it. This is octahedral shear stress. Fine. So this completes the problem, the three sets problem. So let me just quickly revise whatever we have seen today. So first we have started with transformation of stress components. So what will happen when we change the basis from EX, EY, EZ to EX star, EY star, EZ star? We saw that a tensor will transform by obeying the transformation property that Q transpose sigma Q. And when a tensor is transformed, three things won't change. Number one is the trace, number two is the determinant, number three is the trace of the sigma square. And also we saw as per the derivation it is anti-clockwise, so we have to be a little cautious about the sign. Then we saw Mohr circle concepts and how to find the extremum stress using analytical expression as well as the Mohr circle diagram. And finally, we moved on to the 3D. Yeah, we saw some state of stress, uniaxial, pure shear, and so on. Finally, we moved on to 3D state of stress, where we saw how to solve for the maximum principal stress if I am given with a 3 by 3, not a plane stress, a 3 by 3 stress condition. Here we have to form a characteristic equation first. We have to solve the characteristic equation, and then we have to find the directions, principal directions. While finding principal directions, we have to remember that we need the extra constraint, that is the magnitude of the eigen directions is 1. So using that only we can able to solve that equation. Finally, we saw octahedral plane and the normal stress and shear stress in the octahedral plane. Okay. So with this, I am stopping. By the way, if there is any question, please. So, is there any question that you have?
Sir, no, I got everything of this class, but the thing is, sir, I'm having a small confusion. Though. It's not a confusion, but the thing is, sir, when they are giving a diagrammatic, like two-dimensional system,
Okay.
so generally the sigma is a 2 cross 2 matrix, right? Or if in some problem, if they give particularly about the z-axis,
Okay.
there is the first problem they have given 60-degree inclination,
Mm-hmm.
but the with respect to axis is ex. So that's why we considered 2 cross 2 matrix, right, sir?
Yeah.
But in second case, they have given z-axis, the transform 60-degree counterclock direction. So that's why we have considered 3 cross 3 matrix. So another axis comes into picture in that case.
Uh,
Second problem.
Means today, whatever we saw, or in the assignment problem that you're saying.
No, no, no. So now what we are doing here, week three, first problem they have given with respect to ex. That's why we have considered only 2 cross 2 matrix for two-dimensional system. The angle
Mm,
rotation 60
No,
degree
no.
with respect to
Okay,
ex.
okay. I'm okay. Please go ahead, sir. Yeah, I'm getting what you're. I'm trying to see what you're saying. Yeah, yeah.
Yes, yes, sir.
So.
So that's why we have not considered the z direction, Ez, that is sigma z is 0. But
Mm-hmm.
we have directly taken only 2 cross 2 matrix.
Okay.
But in next problem, that is in problem number 2, they have given 60-degree counter the clockwise rotation about z-axis.
Okay.
That's why we have considered the another that is sigma z is one the component also, right?
No, no, that's not the reason. Actually, here
Okay,
itself, I can write 0, 0, 0,
okay, sir.
0, 1.
One. Okay, okay,
Actually,
sir. Okay.
what does it mean, sir? It is rotating about easy axis. Here also, easy axis is there.
There.
Easy
Okay.
is there. And easy
Okay,
star,
sir.
easy, both are same.
Okay, sir. Okay.
EV stand as it is, and
Okay.
only EX EY is rotating about that. So
Okay, sir.
actually, no need to write that third row, third column. If we don't
Okay.
write, or if we write, it doesn't matter because it's a plain stress
Yes.
state. So that's
Okay,
why.
sir. I understand.
In this
Okay, sir. Okay,
question, why
sir.
I wrote, because they were asking EX is XZ, ZX, particularly.
Yes, sir.
So
Yes,
that's
sir. I
why
understand.
we wrote. Otherwise, here
Okay.
also we would have dropped that.
Yes, sir. I understand. So thank you, sir. That's a small
Oh,
confusion
fine,
I had.
fine,
Thank you, sir.
fine.
Thank you very much, sir.
Right, sir. Thank you, sir. Then.
Thank you, sir. Thank you very much.
Right. Yeah.